Out of the box, ROS 2 supports two languages, Python and C++. They are both great, but each has its own advantages and disadvantages. We're going to repeat the same exercise from the previous episode, but with C++ this time. Previously, we built a couple of nodes using Python and made them communicate over a topic using a publisher and a subscriber. This time, we'll rebuild those same nodes and explore the publish-subscribe model using C++ instead. Let's review why you might consider using C++ over Python in some cases. Python is often considered to have easier syntax, which makes it faster to learn and write, making it great for rapid prototyping. Part of this easier syntax comes from dynamic typing of variables. It saves some code writing, but it means some processing overhead and potential runtime errors down the road. You have access to a lot of AI and machine learning libraries, which is great if you want to incorporate them into your robot. Python often runs slower than strictly compiled languages like C++. You can generally expect Python programs to run about 10 to 100 times slower than something similar written in C++. You also have limited multi-threading capabilities thanks to the global interpreter lock, although that may change in future versions of Python. In many cases, writing your ROS applications in Python is perfectly acceptable. However, there are some times when you would want to consider C++. For example, when you need the absolute highest performance or you want low-level control of things like memory or CPU cycles. C++ is a strongly typed language, so you can find some bugs at compile time rather than runtime, as you might for dynamically typed languages like Python. It's also easier to create deterministic programs in C++, although that may mean using a real-time Linux kernel or going to something like micro-ROS. That being said, C++ has a steeper learning curve, and the extra verbosity usually means slower development times. ROS lets you mix and match these languages in your nodes, so you don't have to stick with just one. As we'll see, you can have Python nodes communicate with C++ nodes and vice versa. Let's jump in. With your Docker container running, double-click on the VS Code ROS 2 to bring up the VS Code interface. We can close down any Python code we were working with previously, as we're going to be creating a new package. We can't write C++ files in the Python package, and that's because ROS uses a different build system. We need to keep separate languages in their own distinct packages. So let's go to terminal, bring up a new terminal, let's say config workspace. If your ROS environment is not already activated by something like .bashrc, you will need to run source/opt/ros/jazzy, or the name of your distribution, /setup.bash. I don't need to run that here because it's automatically run anytime I bring up a terminal. You can see in this .bashrc file, it automatically sources that for us. Let's navigate into the source directory, as this is where we want to create our package. We're going to call ROS2 package create. We'll give it the build type, in this case, ament CMake. Ament doesn't mean anything. It's just the name of the build system in ROS2. ROS1 had catkin, and ament replaces that. We also need to specify the language and the build system we want to use. So if you're in Python, that's ament_Python, but for C++, we're using ament_CMake, as CMake is the build system for C++ in ROS2. And we want to give the package a name. We'll use mycpp package, let that build, refresh your files in the viewer. Let's go into source, and you should see mycpp package next to mypy package. Now we can keep our nodes that are written in different languages separate in these different packages. Let's take a look at the folder structure. Include is where ROS will store the public header files that other packages can use. So if we have another package depend on this one, they can look at the header files in here. src, or source code, this is where we will be writing our nodes. We have CMakeLists.txt. This is the build script used by CMake. Recall that ROS uses CMake to build C++ packages. We also have package.xml. This is all of the metadata for the ROS package, like the package name, the version, the author, and so forth. It also defines the build tool. So in the Python version, this will be amend Python, but for C++, you'll find amend CMake. There are some test dependencies. These are ROS packages that this package depends on if you're running tests. You'll see that these are amend linting tools versus the Python syntax checkers. In fact, if I go to the Python version of package.xml, you can see the dependencies here, and these are unique to Python or Python ROS packages. Let's go back to our C++ package.xml, and you can see here where it also lists this build type, which should line up with the tool that we're using. As we did in the Python version, we also need to declare any packages that this package depends on. You can put it anywhere in this section underneath this build tool depend or before this export. I'm going to list it before the test depends. We're not really going to be using these. In fact, you could probably delete them, but I'll leave them here for now because that's what's default. We'll be using XML tags. So that is depend in between some less than and greater than symbols. We will be depending on the RCL CPP package, much like we depended on the RCL Pi package in the previous episode. That gives us access to all of the ROS node source code so that we can do things like subclass a node and build on top of that. It also gives us access to all of the communication details using things like topics and services. You'll also want to list any of the interface packages that you might be using in your code. In this case, we will be relying on example interfaces that comes with ROS2. In a future episode, we will look at creating our own interfaces, and you will need to list them here as well if you create them in a separate package. If you forget to add these dependencies in this package.xml, you will likely find that your source code builds and possibly runs. However, it's considered best practice in ROS to explicitly list the ROS packages you will need here in this package.xml. Let's go ahead and save this. And now we're going to write our publisher. So let's go into source, make sure we're in my CPP package. Let's create a new file, and we're going to call this one minimalpublisher.cpp. We will include the necessary header files from the packages we want to include in this project. In this case, it's rclcpp/rclcpp.hpp. Notice we are using the .hpp header file here for C++. You will likely run into issues if you use the .h version. We also want to use the string interface from example interfaces, and that can be found in example interfaces/message/string.hpp. Then we will create our class. In this case, it's going to be called minimal publisher. The colon here says that we're going to subclass from something else. We are going to subclass from the node class found in the RCL CPP namespace, hence the RCL CPP : Then we're going to define our public methods. In here, we will define our constructor. We'll have it immediately call the node class constructor with our node name, and this is the minimal publisher name that we want to assign it. The colon and then node says to call the superclass constructor or the parent class constructor. Next, we will actually create a publisher object inside of our minimal publisher class. We will use the member variable publisher underscore. In Python, we use the underscore prefix to denote a private member variable or function. In C++, we actually have to explicitly state it as public or private as given by the public or private labels. But by convention, we will use an underscore suffix to denote a private member variable. Here we will say this, referring to this object. Inside of there, we will say create publisher. That's because the node superclass has this create publisher method in it. We will use a template here, given by the less than, greater than symbols. Inside of that, we will give it a type. In this case, the example interface's message string. So in the example interface's namespace, there's a message namespace, and in there is a string class that works as a type for this template, so that create publisher knows what type of interface to use because it's based on this string class. For the arguments, we'll pass in the name of the topic, in this case, my topic, and then we can either pass in a quality of service profile or in this case, a simple depth integer. so it remembers up to 10 messages. Before we continue in our constructor, let's go ahead and declare that publisher variable. We will create a private section where we will put our private methods and member variables. In the RCL CPP namespace, there is a publisher namespace. We can use this template again to say that we want to use a string type for this interface. That's because publisher is a template class, so we have to give it that specific type. And this : shared pointer is a type alias to give us a standard shared pointer. A shared pointer is a form of a smart pointer. This was introduced in C++ 11 and is considered crucial to many modern C++ practices. This helps prevent memory leaks and dangling pointers, as the memory is managed automatically for us. The resource is deleted when the smart pointer goes out of scope. In general, you want to use these instead of malloc and free or new and delete that you might have seen in older versions of C++. There are several types of smart pointers, but we'll be using shared pointers in this ROS2 series. A shared pointer allows multiple owners. The resource is deleted once all of the owners are finished using it. This is opposed to, say, a unique pointer where there can only be one owner. Let's go back to our constructor, and I'm going to close this terminal so you can see what's going on here a little more easily. Next, we're going to periodically call a method. We're going to do this by creating a timer. While the Python method is createTimer, this one we want to create wallTimer, as that allows us to elapse a specific amount of milliseconds or seconds based on actual wall time. Once again, we're referring to this, which is a built-in method in the node parent class. The first thing we pass in is the amount of time we want to wait between calls. std : stands for the standard namespace. This is a standard library that's been included in C++ 98 and versions after. Standard chrono was a library introduced in C++ 11. And we also have standard chrono duration. This is a template class that represents a length of time. So we can use standard : chrono : milliseconds as an alias for a particular duration. And we can just pass in the number of milliseconds we want. This will automatically convert it to the correct duration type that gets passed into this wall timer. We also have standard bind. Here we pass in the function we want to call, and then a reference to this. This creates a new function-like object that can be called later. This is also known as a functor. We have to give it a pointer, hence the ampersand before minimal publisher. This is a pointer to a non-static member function to call, so it's got to be a function in this class. We will create the timer callback function in just a moment. And then this tells the RCL CPP timer which instance to call the function from. So this will refer to whichever object has been instantiated from this class. So we could have multiple versions of these nodes running. This will refer to a particular instance. We should also declare that timer member variable. So down below in private, we will write RCL CPP for the namespace, timer base, that's a class in RCL CPP, and then shared pointer, which is another alias. That gives us a shared pointer to a timer object. Like we did in Python, we will use a member variable to remember the number of messages sent. So we're just going to store that in a counter. We also need to declare this member variable. So in private, we will say size t, counter _ semicolon. Size t is generally used to represent sizes, counts, indexes, and so on. It's fairly common in modern C++. It also handles adapting to the 32-bit or 64-bit systems, where we might have to worry about that if we're using something like an unsigned integer. So generally for things like these types of counters or array sizes, size t is the go-to variable type. Then in private, we will write our private methods. Here, let's define our timer callback. We will construct our message. In this case, we will use the example interface's namespace in their message and then that string type. The variable name is message, and we will use this auto type. Again, this is a fairly new feature in a lot of modern C++. This allows the variable to automatically figure out what type it is based on the return type of the function or object being instantiated on the right side of the equal sign. We will access the data field in message, and we will set that to the string hello world, followed by whatever the value is in counter. The standard library has this toString function, so we just pass in this integer or size t. It will convert it to a string and concatenate hello world and that value. Then we will access the publisher object and call the publish method in there, pass in the message as our argument. Just like logging to the console or the log files in Python, C++ has something similar in ROS2. There is this RCL_CPP_info or error, warn, whatnot, whatever level you want for the debugging message. That is a macro, and we pass in a few things. The first thing we have to pass in is this logger object, and we get that by calling getLogger, which is part of the node superclass. Then we can pass in the actual string. In this case, we'll say publishing, and then whatever data we've been publishing. So to fill in that %s placeholder, we will say message, which is our message we created, .data, which is the data field that's been filled out. And then all of those fields have a .cstring function that we can call to convert it automatically to a C string that works for filling out these string placeholders. Finally, we will increment our counter. We need to define an entry point. Like any good C++ program, this should be called main, and it should return an integer to let the calling process or the runtime know if the program succeeded or failed. A common signature you will see for a lot of C++ programs includes these parameters argc and argv. Argc is the number or count of arguments that the command line has passed in, and argv is the argument vector. This is an array of C-style strings, so character pointers, that you can then parse in your program should you want to use parameters from the command line. While you can parse them yourself, ROS2 handles that for us, so all we have to do is pass them in to this init function that's part of the RCL_CPP namespace. Then we will initialize and run our node. We will once again use that auto type because we will be calling makeShared, which creates a shared pointer. This is from the standard library that's just automatically part of C++ these days. This uses a template in order to create a shared pointer to a particular object type. In this case, we will say minimal publisher, which refers to the class we just created. We don't pass in any arguments. Auto will have a shared pointer to an instance of our minimal publisher class. From there, we will call the spin function in RCL_CPP and pass it in the node we just created. That spin will, in theory, run forever. But if we Control-C or something else stops it, we should call this cleanup function, which deinitializes the ROS2 runtime environment. And then we want to say return 0. 0 in this case means that the program has successfully executed and exited. Unlike in Python, there's no need to manually catch something like Control-C. In the ROS2 C++ runtime environment, Control-C signals are caught automatically, and spin is unblocked. This is what causes execution to continue down to that shutdown call. By using smart pointers throughout this program, memory is automatically deallocated. We don't have to do anything special with destructors or freeing up memory. Let's save this, go to terminal. We'll go to a new terminal in our workspace. We'll call colcon build, and we'll say packages select my CPP package. This should build just the CPP package. This should finish with no errors. If we look in the workspace folder, we should see these folders again. In build, you should see, in addition to my Python package, you should see my CPP package. This contains compiled objects and any intermediate files used by colcon during that build process. The install directory contains executable binaries, shared libraries, and message interfaces if we created any. Then we have log. This is logs of your builds and any tests that you might run. Now let's go to a new desktop and we will open up a command prompt. As we have been doing, we will use the terminal in VS Code for building, and then we will use this other desktop for running and testing our nodes. Here, let's try to run our node. We'll call ROS2 run my CPP package minimal publisher. You should see this, my CPP package not found. That means that we have not sourced the correct environment, so ROS2 is not aware of our custom package. Even though we've sourced the environment in .bashrc, that gives us access to things like ROS2, colcon, and the built-in packages, but not our custom packages that we've been working on. Let's navigate into config workspace, and we will source from the install directory setup.bash. Now, I'm going to push up a couple of times to get back to this ROS2 run. Let's try this again, and no executable found. Just like what we ran into in the Python version, we need to register the executable. Even though the package was found when we sourced the environment, the executable had not been added to our build script. So let's go back to VS Code. We will go into CMakeLists.txt. Up top, you should see the CMake required version, the minimum version, and a name of our package, in this case, my CPP package. This has been filled out for us when we did that ROS2 package create. This sets up some compiler flags, and then we tell the ROS C++ build system to find some various dependencies and packages. So we can get rid of this here, and we need to add a couple here. Just like we added for package.xml, we need to say we are dependent on the RCL CPP package, as well as we are dependent on the example interfaces package. Recall that package.xml is used to describe the overall ROS package and any other ROS packages that it is dependent on. In CMakeLists, this is required for the build system. So here we need to also say we are dependent on the RCL CPP and example interfaces packages. We won't be working with testing this time, but this includes any testing scripts or dependencies if build testing is set. Before we define our package at the bottom, we need to do a couple of things here. The first is we use this CMake function add executable that creates an executable target for us. In there, minimal publisher is the name of our target that we will be building for, and then we need to tell CMake where to find the file to build. From this CMakeLists.txt, wherever that is in that directory, it should look into the source directory and find our minimalpublisher.cpp. Previously, we told CMake where to find particular packages or had it go and find those for us. And now we actually say that a particular executable is dependent on those specific packages. In this case, we will be using ament target dependencies. This is a ROS2 specific function created for CMake. It says to link the RCL CPP and example interfaces libraries to the minimal publisher target. Then we need to tell CMake where to install the binaries once it's done building them. So we will call this install function. We need to tell it that we are going to be installing specific targets, hence this keyword targets, and then the name of those targets, in this case, minimal publisher, which we just defined above. And then we define a destination given by this destination symbol, and we tell it where to put it. ROS wants to put it in lib/ and then the name of the project. You can get the name of that project by this line 2 here. So the project is named mycpp.pkg. So CMake will put it in there, and that's where ROS2 expects to find those executables. Let's save that. Let's build again. So I'm going to push my up arrow, colcon build, packages select, mycpp package. We will let that build. And it looks like I got an error. As per usual, I forgot a semicolon. I probably forgot it after my class. So if I control click on this, it will take me to the spot of the error. And I scroll up, sure enough, there's my class definition, and I forgot a semicolon after the class definition. Let's save that again, push up arrow in the terminal, try to run colcon build. It looks like we succeeded this time. So let's go back to our run environment. I'm going to push the up arrow and run the minimal publisher again. Sure enough, we see that publishing to the console. Let's bring up a new terminal, and we will say ROS2 topic list. We can see the available topics here, and we can say ROS2 topic info / my topic, as that's what we're publishing to. You can see the type there, and you can see the number of publishers and subscribers. So we will say ROS2 topic echo and the name of that topic. That creates an instant subscriber, so we can see what's being published to that topic in real time. Let's press Ctrl+C to stop both of these. And we will head back to VS Code to write our subscriber. In src, let's create a new file. We will call this minimalsubscriber.cpp. We will include the same header files as we did in the publisher, in this case, rclcpp.hpp and string.hpp from example interfaces/message. As we did with our minimal publisher, we will create a class called minimal subscriber that inherits from the parent node class given to us by rclcpp. For our public functions, we will just define our constructor. In the signature, we will say :node and the name of our node. That automatically calls the parent class constructor with the name of the node. In this case, we want to call the node minimal subscriber. Then we will create a subscription object, similar to how we created a publisher object. We will call the create subscription function. That's a method found in the node parent class. This uses a template, so we need to give it to the interface type, in this case, example interfaces, : message, : string. We need to give it the name of the topic we want to subscribe to. This should match the same one found in publisher. So we will say my topic. We'll give it either a quality of service profile or just a simple depth for the number of messages that it's allowed to queue up. So we'll say 10 here. And then we want to call this standard library bind function. This creates a callback function. So we pass in a pointer to a function, in this case, a method that's going to be a private function in this class. We'll call it listener callback. This is so that when a message is received, this function will automatically be called for us. So we will create a pointer to this listener callback function that's going to be part of our minimal subscriber class. We will create that in a moment. We need to pass in this, as that points to a particular instance of this class or an object. And C++, the standard library in C++, has this handy placeholders feature. So this placeholders namespace has a number of placeholders known as _1, _2, _3, and so forth. This is how we define parameters for callbacks. So when ROS2 calls this callback because some message was published to this topic we're subscribing to, it will pass in the message. We don't know what that message is yet, so we can't pass in an argument. So instead, we use this placeholder, and then ROS2 will fill it in later for us. That's all we need for this constructor, but let's go ahead and declare our member variables. We'll define our private section for our class here. As we did for our publisher, we will use this shared pointer that's found in the rclcpp library. So in that namespace, we have the subscription class, and this is a template class, so we need to provide in a type. As you saw with publisher, we will provide the example interfaces message string type, so it creates a pointer to an object created with that type that's been passed in, so it creates a subscription with that particular interface. The shared pointer is an alias for creating a shared pointer to this object, and we will store it in this variable called subscription _ so that we know it's part of this class. It's a private member variable in our minimal subscriber class. And just so we're obeying the 80 character column limit, I'm going to put this on the next line. I'm going to save just in case. And then let's go down below private again, above our member variable. We're going to create our callback here. We're going to call it listener callback, so it lines up with what we bound earlier to that subscription object. And we're going to expect a message as our parameter. In this case, we're going to expect a pointer to our message. We'll use the keyword constant so that we can't change the message once it's been passed in. And we expect type string. That's part of this example interfaces namespace. The ampersand means we are passing in message by reference, even though we can't modify it. If you want to avoid writing all of these namespaces with these double colons, you are absolutely welcome to use that using keyword at the top of your file here. That will save you on a lot of entering these types. I'm just being explicit with my namespaces here so you can see where the types for these variables belong. Just like we saw in Publisher, we can print something to the console. In this case, we're just going to print out the message we received. We will use rclcpp.info, this macro, to log it to the console as well as to any logs that you set up. We need to pass it in an instance of the logger that's been created on the backend for us. And we will also provide the argument of received message and then fill out the message data.c string that we saw in the Publisher example. Let's not forget the semicolon at the end of our class definition. And we will provide another entry point. This is going to be our main function. As we saw earlier, we will call init in RCL-CPP. We will pass in the command line arguments. We will then initialize the node using that make shared function that's found in the standard library. We will pass in the type minimal subscriber to this template, and we will use auto so that the node variable automatically figures out what type it needs to be. Then we'll call spin in RCL-CPP, pass it in the node, so it just runs the node as its own process. If we exit spin because we, for example, pressed Control-C, we will perform any cleanup by calling this shutdown function. And like any good C++ program, we will return 0 to denote that everything returned and executed correctly without error. Let's save this with Control-S. And we need to go into our CMakeLists.txt to add a new executable. We will add this executable target known as minimal subscriber and point it to the minimal subscriber.cpp file that we just wrote. Then we will call this ament target dependencies function, tell it the target that we are building for, and give it the dependencies or the libraries we're using in that target, in this case RCL-CPP, and example interfaces just like we did for the publisher. Finally, we need to add it to our binaries. This will tell CMake where to install our executables once it's done building them. Press Control-S to save it. I'm going to go to View, Terminal, to bring up the terminal we've been working in. And I'm going to say colcon build -- packages select and give it the name of this particular package, my CPP package. With any luck, that should build successfully. You should get this nice little green icon here. Let's go over to our run desktop. I'm going to push up in the terminal on the left to start running the publisher again. And then in the terminal on the right, let's go to config workspace. Let's source install setup.bash. And we will run with ROS2 run my CPP package minimal subscriber. With any luck, that should subscribe to my topic and start printing out the messages it receives on that topic. What you see in the subscriber should line up with what you see from the publisher. Let's open up a third terminal. I'm going to move this over to the bottom left here, and I'm going to call RQT graph. Right now we just see the subscriber. I'm going to refresh, and you should see the publisher publishing to minimal subscriber on my topic. I can say nodes and topics. That should put topic in a rectangle, which makes it a little easier to see what you're doing with those particular nodes. Let's go to our second terminal here. I'm going to press Control-C to stop that subscriber. And then I'm going to call ROS to run my Pi package minimal subscriber. So now we're going to run the minimal subscriber we wrote in Python from the previous episode in this terminal. That should fire up. And you can see it is receiving messages from this publisher. These nodes are the same. So if I refresh, you see that the nodes are the same in RQT. But the publisher was written in C++, and the subscriber in this case was written in Python. Hopefully you start to get a sense of how nodes can be written in different languages and still be able to communicate with each other in ROS2. Let's press Control-C to stop both of these. If you want to learn more about RCL-CPP and a lot of the classes and functions you can find in this library for controlling a lot of ROS elements, head to docs.ros.org/en/ the name of your distribution, so Jazzy for us, /p/RCL-CPP. From here, go to C++ API, and you can learn about the node class, the publisher and subscriber that we created, the timers, and then services, which we will start talking about in a future episode. Remember that you can't press Control-C to end the container. You either need to go to containers in Docker desktop and press the stop button. That will stop your container and clean up any resources. Or from your command line, you can just exit out of your command line. That should stop the container. And because of that -rm flag we passed in when running this container, it should clean up everything. Or if you go to a new shell, you can type docker ps to list the processes, docker stop, and you can copy this container ID, and that should shut down the container automatically for you. Here you can see the container has stopped. No containers are running, and we can't access that site anymore. You might have noticed that I kept most of the variable and function names the same between the Python and C++ example nodes. Hopefully this helps you see how creating nodes is similar between the two languages. In the next episode, we'll go back to Python to demonstrate how to work with services, requests, and responses.